And of course, as soon as you start, my computer falls asleep. Okay. So yes, thanks everyone for coming. My name is Avi. I'm a researcher at the University of Auckland. Thanks, Mitchell, for introducing me. And I work on gravitational waves. Specifically, I try to hunt for black holes using gravitational waves and machine learning techniques. And today, I'm going to talk a bit about my research, but I'm going to actually talk a bit more about how we even came up with the idea of gravitational waves, where the idea of black holes came to be, and kind of avoid the nitty-gritty maths and just get, go back to the concepts. So I want to start with my trip to Dublin. Last year, I went for a conference in Dublin where we were talking about black holes, and after the conference, I had some time to wander the streets, and I found this really cool secondhand bookstore. And I think this bookstore was affiliated with the university because there was like a ton of these old textbooks at the bookstore. And they were just beautiful, these textbooks which were clearly well used and well loved, but now they were trying to find a new home. And there was one textbook that I found there that was called Modern Astronomy. And it was published in 1901. And I think my favorite thing about this book is I flipped it open immediately, right? And I wanted to know what modern astronomy was in 1901. And on the first page itself, it was, in the preface, the author was talking about this idea that, we now have photographic film. We can now photograph the entire night sky. Astronomy is basically going to be done in a matter of 10 years, right? With photographs, we're just going to photograph everything and it will be done. And in one of the, a few pages down, I took a picture of this because, you see this? It says, the Great Nebula in Andromeda. So what's fun about this is that back in 1901, we didn't know that Andromeda was a galaxy. We thought Andromeda was a nebula within our own Milky Way. And what's also amazing about this is that, again, we thought that astronomy was done, right? And we were quite wrong back then. Because we now know that Andromeda is actually, not within our Milky Way. In 1901, we thought our Milky Way was our everything. We thought the edge of the universe. We thought this was the universe, right? And now we know that's not the case. We now know that Andromeda is quite far away from us. And we only discovered this in 1920. And I think that's quite amazing to think about, right? The fact that we only learned that Andromeda was not in our own galaxy, but a separate galaxy. The fact that we learned that there were other galaxies out there just in the 1920s, right? And it's amazing, again, because Andromeda is actually, it's been visible to us, since for all mankind's time. In fact, if you go out driving, I'm guessing some of you are into astrophotography, yeah? Some of you, maybe? You can actually you probably already taken photos of Andromeda. In fact, in New Zealand, if you drive out to a dark sky reserve, you can see Andromeda as well. That little dot there is Andromeda. 2.5 million, it's really far away, and yet we can see it with our own eyes, right? And we had no idea what it was. In 1920s, we finally figured out that it was its own galaxy. And I tried to actually go to the pinnacles in the Coromandels with my friends sometime a few months ago, and we climbed up, and I was really hoping we'd be able to see it, but the clouds had other plans. So unfortunately, next time I'll get this photo. But this photo was specifically taken by Tirangi. I think it's someone from Facebook. It was someone, I think they took this photo in a place called Onmana? Yes, thank you. And, but yeah, again, I guess I want to highlight this idea that, this discovery that there are these other galaxies out there, right? This, in the 1920s, this shifted our perspective of space. Before this, our idea of space was much, much smaller. It was we kind of understood, what space was. We understood the Milky Way. But then, in the 1920s, this concept of the universe just blew up. It expanded so much. Humankind immediately, overnight, became an even tinier drop in an even larger ocean. There became these billions and billions of these tiny little, oh, come on.
Yeah, it does.
This bit, yeah. Sorry about that.
We'll get it.
Yeah, there's like, we found that there were tons of these other galaxies out there, of these tons of things that, we didn't know about. And I just find it so beautiful that we only truly learned the scale of the universe like about 100 years ago. Right? I think that shows us how young astronomy and astrophysics really is, and how there's still so much to learn. If we just 100 years ago, we found this out. Right? And I think that's again highlighted when we look at black holes. Right? Because black holes, in 1901, the concept of black holes didn't even exist. We didn't think about them. They weren't even in our minds. And only in the 20s did they become these theoretical curiosities. And actually in the 20s, people didn't like them. Albert Einstein, he hated them. He was like, what are these, it's basically something that breaks my equations. He doesn't like it. So physicists at the time were like, nah, let's ignore this for now. And so it took a while. It took a while until the 60s. And in the 60s, we had more astronomers coming back to this idea. We actually had Kiwi astronomers. We had someone called Roy Kerr. So he's in Canterbury, and he's a genius. He actually worked a lot on the theory. He, along with Stephen Hawking and Roger Penrose, they worked on the math together, and they were able to show that these black holes aren't just, they could actually exist. Theoretically, they work out. They're not just mistakes in math. They could actually be real. And then, finally, in the 70s, they find the first candidate for a black hole. Right? So it was only the 70s. And again, the 70s, that's actually after we've already landed on the moon. So we learned about like the first candidate for a black hole in the 70s. But that was still just a candidate. It's like a hazy kind of idea that there could be a black hole. Only in 2015 do we have the first concrete, indisputable evidence of a black hole. And that comes from a gravitational wave. So in 2015, we detected the gravitational wave from two black holes that were spiraling into each other, and they merged. They generated these ripples in the fabric of the universe, which eventually reached us. And with those, when we detected those ripples, we can try to convert them into sound. And hopefully this plays. This is the clip of the first gravitational wave event. A bit. Yeah. So yeah, and okay, so I know that sounded like really staticky and a bit noisy and very loud, but that was the first signal that we got, right? And maybe it was hard to make out, but there was the little blip right at the end, and that was the sound of the two black holes actually merging, right? And again, it might just sound like a bit of static, but I truly think that that clip is one of the most profound discoveries of our time, right? And it's kind of like, when humanity first figured out that the world is not flat and it's actually round. Some may still argue this, but let's stick with the idea that it's actually round. When we first figured that out, that piece of knowledge, that piece of knowledge had so many knockback effects, right? Immediately, as soon as we figured out that the Earth was round, we were able to change how we navigated the Earth. We changed how we shipped goods and ideas and people around the Earth. And for better or worse, the world was transformed forever, right? Once we get a piece of knowledge, there's almost like no going back. Why would you want to go back now that you know more? And that's the same with gravitational waves. Gravitational waves have opened up a new pathway for us to look and engage with the universe. They've helped us find these black holes. They've helped us learn about these black holes. And so today, I'm going to try to explain to you why I think that sound clip was one of the most profound discoveries of humankind. And I also want to explain a bit about how we came up with the idea of these gravitational waves. And my objective is to hopefully, by the end of this talk to firstly convince you that black holes aren't really holes, but they're actually these mountains of dense matter that form when stars die. And that, secondly, astrophysics, black holes, gravitational waves, this entire field is very young. The mere fact that we've only discovered the first concrete black hole in 2015, it's like 10 years ago, right? And then thirdly, that gravitational waves is giving us a new perspective to look at the universe. So to start off, I wanted to take us all the way back and take a closer look at gravity and the origins itself. And come back to how we came up with the idea of gravity. We have to go back to Isaac Newton. So Isaac Newton, this man was an absolute genius, right? He mathematically described how two objects with mass attract each other through the force of gravity, right? He was able to write down equations for gravity, and he was able to also demonstrate that these equations kind of worked for the planets in our solar system. So he looked at a bunch of the planets, and he plotted how they moved, and he tried to make predictions for how they should move based on his equations. And it worked really well up until Mercury. So for Mercury, for some reason, his equations just were not predicting the exact motion. And he was kind of bugged why. He's like, it should work, but it just wasn't. And he wasn't quite sure why it wasn't working. And he also wasn't quite sure why his equations for gravity actually worked in the first place. So what is it about mass that attracts other mass, right? So these questions kind of really bothered him, and it plagued him. And he tried to think about it, but he wasn't really making much progress. And in fact, it plagued a lot of scientists for many years, for decades. And actually, it took centuries until we actually made any substantial progress. And only in the 1900s did we actually finally start taking steps forward. So in 1906, Einstein had what we call his miracle year, right? He published his theory of special relativity. And I won't go into too many details about this theory, but one of the main ideas is that there is a speed limit to the universe. There's a maximum speed at which information can travel. And this speed is the speed of light, right? And this, he wrote down his equation, he wrote his theory, and then he said that there should be the speed limit. Okay, and if we all, right for now, just take this idea of this maximum speed limit for the universe, he started thinking about this and then thinking about gravity. Oh, come on. Yeah, I'll just poke it around. And the reason he thinks it breaks gravity is because, okay, so according to Newton, anything with a mass has a sphere of influence around it, right? So anything with mass will affect other things with nearby. And as you move it, that sphere of influence will move instantaneously, right? And that's what he was a bit upset about. So Einstein really liked doing these things that he called thought experiments, right? Where he would come up with an image or a scenario in his head, and he would just let it play it out. So I want all of us in this room to run one of his thought experiments together. So imagine that, yeah, we have the sun, and we have the Earth that's orbiting the sun. And now, just thinking of Newtonian physics, what would happen if we take the sun away? What would happen to the Earth's orbit once we take the sun away? So anyone want to hazard a guess? Yeah? Straight line? What were you going to say? The same thing? Yeah, you both are exactly right. So the Earth would go straight off on a tangent, almost like you're spinning a stone on a string, and you let go. The stone should go where it last was, right? It just goes straight off. But there's an issue. That would, in a way, mean that the information of gravity disappearing reaches the Earth faster than light. It takes light 8 minutes to reach us from the sun. So the fact that gravity disappears, it should also take 8 minutes. But nowhere in Newton's equations is there any concept of time, right? There's no concept that gravity is somewhat affected, It should happen instantaneously. It's an instantaneous force. It is like a string that's attached between two objects. And this breaks Einstein's theories of relativity. And so Einstein's perplexed by this, and he's like, okay, hold up. We gotta roll it back and start working on the math again. Let's take gravity back to the scratch and work all the way back up and try to see if we can figure out where this time thing comes in. And he then spent the next 10 years working on his new theory called the theory of general relativity. So it's kind of an extension of his initial theory. And in this, he kind of described how he described the set of equations in which he could think gravity can work. Now, the most interesting thing is that when he wrote down his equations, in the process of doing so, firstly, he also kind of helped improve this branch of mathematics called tensor calculus, which is actually what we use in machine learning and ChatGPT nowadays. So we can thank Einstein again for ChatGPT, I would say. But when he finally finished his theory, he ended up with a set of equations that he himself wasn't able to solve, which I think is amazing, right? Like imagine that you're a professor writing an exam paper for students, and you write this exam that you yourself do not know how to solve. That's kind of what Einstein did, right? And then he started lecturing about his theory of general relativity all over the place. He started pitching it at various universities and talking about it to anyone he could explain it to. He wrote about it in the papers. He told everyone about it, and he was asking for help. He was like, "Yo, please help me out. Like, I don't know how to solve these equations." And that's when we get Schwarzschild. Yeah. So Schwarzschild was a German Jewish scientist who joined the army in World War I. And during the war, he was stationed in the Western Front up on the mountains. And unfortunately, during the war, he got really sick. He got so sick that he wasn't actually able to still perform his duties as much anymore on the war front. And so he was bedridden, and while bedridden, he started letting his mind wander into these new theories and equations that were being proposed by Einstein. And even though he was in pain, under medication, he worked through the math, and he figured out something that could work. He thought he had an idea that could work, a way to solve Einstein's equations, a way to solve Einstein's exam paper, and he sent back his solution. And I really love this quote. So in Schwarzschild's, I hope I'm pronouncing it right. Am I pronouncing it right? Schwarzschild? Schwarzschild. Okay, so sorry, forgive me. So it's so he sent his letter back, his equations back to Einstein, and at the bottom of the letter, he had this quote written, and I think it's beautiful. He says, "As you see, the war is kindly disposed toward me, allowing me, despite fierce gunfire at a decidedly terrestrial distance, to take this walk into your land of ideas." And I just think this is such a beautiful way sometimes that physicists can think. They can look at these equations and they can just lose themselves in the beauty of the math. And I'm not quite there yet, but I'm glad that people like him exist to do the math for us. And so he sent off his letter to Einstein December 22nd, 1915. And Einstein receives it, and he works through the math. He double checks the solutions that were provided, and he's like, "Oh my gosh, this works. This makes sense. It all works." And so Einstein also writes back. He basically writes back saying that I liked very much your mathematical treatment of the subject, right? And I think it's a beautiful little exchange that they have. And Einstein's super excited. He says that he wants to present Carl's work, of course, acknowledging Carl's, that it is Carl's work. He doesn't steal credit. He goes and presents this work to various groups immediately, right? This is January 9th. And Einstein writes back to Carl, being like, hey, like he wants to keep on working and coming up with some new papers and stuff. But unfortunately, Schwarzschild's his illness kind of got him. I guess this is again why war is just really lame, because we had this brilliant mind and he was caught up in the war, and he just he wrote 3 papers, but he was in the infirmary. He wrote 3 papers while he was so sick. And if he just managed to spend some more time, if he and Einstein had some more time together, I just wonder what kind of amazing things they could have come up with. Right? But Einstein now had these solutions, and he wanted to continue with them. He wanted to try to use them. And so Einstein took, okay, actually, let's take a step back and try to figure out what is the solution that they come up with, right? So Einstein's theory and Schwarzschild's solution is kind of hard to picture, but astronomers very often like to describe it almost like a trampoline. So imagine that you're standing in the center of a trampoline, right? When you stand in the center of the trampoline is going to have a little bend where you're standing. And now imagine that someone's rolling a ball next to you. As the ball rolls, because of the dip that you've caused, the ball is going to start spiraling inwards, right? It's going to almost like a funnel. Now, this is different from what Newton describes. If you're standing on in a Newtonian plane, it's like the gravity is not going to affect that way. If you roll a ball, it's just going to go off straight. There's no bending of space. And so this is kind of what Einstein's and Schwarzschild's solutions are talking about. And the idea is that if you actually move matter on this fabric of this trampoline, that's when you can get these gravitational waves. But we'll come back to that a bit later on. So this is the concept of space-time, and Einstein takes this concept of space-time. How are we doing on time? 30. Okay. Yeah. So he takes this concept of space-time, and he tries to apply it the same way Newton applied it on the planets' trajectories in our solar system. And he's able to get all the planets, including Mercury this time. So Mercury has this really funky-looking orbit. It has what we know as like a perihelion precession. It kind of makes this flower-like pattern. And Newtonian physics was not able to describe it too well, but Einstein's new general relativity describes it to the dot. And this is happening because the sun has, this is causing this distortion in the fabric of space-time, and Mercury is kind of tracing that path out. So this was a pretty cool test, but people weren't really too excited by this. And so the theory was really complicated, and people were like, oh, okay, cool, you have a theory of gravity. But it didn't really catch on. It was only until 1919 when we had a British astronomer coming in and helping out. So I think this is also kind of amazing, right? Because this is a German scientist, and this is a British astronomer. And at this time, Europe is not like in the best politics is happening. But it's cool that science doesn't care about that stuff, right? Like this is a British guy helping out a German guy with his science. And what Arthur Eddington does is he decides to head down south to Africa. He voyages down south, and his idea is that he's going to take a picture of the Pleiades, Matariki, right? He's going to take a photo of it, and then he's going to wait for 6 months because he knows there's going to be a solar eclipse, full totality. And the idea is that, according to Einstein, because of the curvature of space-time, light from Matariki should bend around the sun and still reach us. If it was Newtonian physics, light shouldn't bend. Light would just go straight and be blocked by the sun. And so Eddington was willing to trust Einstein's equations, and he stayed there for 6 months. He made the gamble, and he hoped and prayed that there would be no clouds, because no way would he have enough funding to do it again. And he was lucky. He was able to wait, stay, take the photos, and he could see the stars, even though they shouldn't have been visible, because the sun should have been blocking the stars. The sun was in front of the Pleiades. It was in front of the Matariki constellation. And yet, the light from those stars was still visible because it had bent around the sun because of general relativity. Arthur Eddington heads back to the UK and he presents this work. He tells Einstein about this. He tells everyone, right? He presents this work, and the very next day, the newspapers around the world blow up. This is my. I'm gonna put up New York Times headlines. This is my favorite headlines. There was quite a few, but this is one I picked. Lights all askew in the heavens. Men of science more or less agog. What is this? Stars not where they seemed. This is my favorite part. Nobody need to worry. I like that the newspaper has to say this. They have to like tell, okay, it's fine. It's just scientists being scientists. Einstein just doing his thing again. Just don't worry. It's, it's cool, but yeah, it's all good. And I love this, right? And this is kind of what, through Einstein, this is what catapulted him to the level of fame we know him now, right? This is what made him Einstein. This is what made him so famous. And okay, I also have one more picture. So in like a few pages later, they have actually an infographic of the experiment. I kind of love like old science history stuff, and so I love this image. So yeah, the idea was that it should have been the straight line, but it actually ended up being a bit bent, and the positions of the stars was slightly changed due to general relativity. So yeah, it's kind of amazing. And so, most of the people around the world were really, kind of excited by this. Einstein was really famous now, and he was happy that his theory was being accepted, and people were listening and reading into his work and trying to understand it and engaging with it. Scientists love when people actually listen to them and actually try to build off on their work. And so he was excited, right? But there was something in Einstein's work that really kind of got him nervous. Because when he looked at the equations, he saw that there was something about it that spoke about a possibility for something with infinite mass. So in the equations, it basically said that if there's something with bigger and bigger and bigger mass, that dip in that trampoline can go deeper and deeper and deeper. And nothing in the equations prevented this. But to Einstein and other physicists at the time, this just didn't make sense, right? Like, there can't be something with infinite mass. There can't be like this hole in our fabric of space-time. It made no sense to them. And to them, those solutions were meaningless for physics. It was a bug. It wasn't a black hole. It was just math, not behaving, right? And they didn't like this idea. They thought it was nonsense. They just waved it away. To them, the theory was just a bit broken. To him, his equations were a bit broken, so he was a bit upset by that. What's funny is that even till now, we're still trying to we're still trying to break his theory, and we can't. So he thought his theory was wrong, but he was actually right. Even that bug, it was actually right. But around the same time, when these experiments were going on, and Einstein was publishing his theory, and all this was happening in the UK, there was this kid in India. He was 10 at the time. He started reading into physics, and any new physics material he could find, he would try to get his hands on it. And soon he became old enough to, whoa, I was not happy with that. Soon he became old enough to apply and head to the UK for his PhD. So he got accepted into a PhD program at the age of 19. He was heading over, and his head was already up in the clouds. He had fallen in love, similar to Schwarzschild, with Einstein's equations and his world of mathematics, right? And he had also been trying to look into any physics he could. So he was trying to connect nuclear physics with astrophysics and trying to just try to get as much information into his head as he could. And on his journey from India to the UK, he started thinking about some of the math that was presented in these papers. And he started thinking about stars. He started thinking about what happens when a star burns out all of its fuel. What happens when a star fizzles out? And he started thinking about just things like, okay, if we have a star and it burns up all its fuel, what actually remains? Do we still have a star? What's, like, he started to write down the equations for this. And in his equations, he found this strange maximum limit. He showed that there's this maximum limit for how big a star can be as it fizzles out. This is now known as a Chandrasekhar limit, right? And this was pretty amazing to him because it was strange that, like, math showed that there's this limit to how big a star can be. And he arrived in the UK. He told his advisor about this, and he's young still, right? He's 19 years old. He told his PhD advisor about this, and his advisor was quite encouraging. He told him, "Oh, go present this. This is interesting work. Go present this." And Chandrasekhar went, and he went to a conference, like almost like a month after he started. And he went to a conference where he presented this in front of like a crowd full of physicists, and he could see his role models in the crowd. He could see Eddington, the person who helped Einstein take those photos. He saw other big physicists in the crowd, and he presented his work on the maximum limit of the star. And unfortunately, Eddington was not so receptive. He took Chandrasekhar's work, and right after Chandrasekhar presented, he presented what his thoughts were in a very unprofessional manner. He got up on stage and called Chandrasekhar's work stellar buffoonery. This was just tragic, right? Because this man, who was like almost like a god to Chandrasekhar, gets up right after him. He's a well-known physicist at the time, 50 years old, well-respected, gets up and just ridicules Chandrasekhar. Doesn't even basically he then spends the next 10 years just belittling and trying to tear down, and not in a scientific way either. There's been quite a few articles about how the work that he single-handedly managed to do, he kind of bullied Chandrasekhar out of the field. Chandrasekhar, unfortunately, felt so humiliated and so belittled that he changed his research goals and trajectories. And it's really tragic because he was right. He was right, and people just weren't willing to listen. People weren't willing to actually just try it out and be scientific and go through the scientific method as scientists should. They listened to the one big man, the big old white man, and they were like, yeah, his word is gospel. Thankfully, Chandrasekhar was later acknowledged for this work, and he got the Nobel Prize, but he was bullied out of the field in a way. There were some, though, that didn't listen to the masses, and they did actually try to follow on and build off Chandrasekhar's work. It did take some time, but in about 10 years, Oppenheimer comes along and builds off of Chandrasekhar's work. So Oppenheimer, along with his student Hartland, they kind of looked at Chandrasekhar's work, right? And they saw that, okay, Chandrasekhar talks about this maximum limit for a star, how big a star can be. They wanted to see what happens above this limit. Why is it that there has to be this maximum mass for a star? And he publishes this paper on this idea of a gravitational collapse. And I think it's a really beautiful idea, and it's still what we use to understand stars today. And how it works is you can think of a star like a balloon, right? And you have this balloon. In the center of the balloon, you have some fuel that's burning. And this fuel that's burning is what keeps the balloon afloat. So the fuel is burning and is pushing outwards. That's what's happening here. There's pressure that's pushing outwards and keeping the balloon alive. And then as you're burning the fuel, you're building up waste product, right? This waste product then settles on outside the balloon and presses inwards. And so you have this kind of interplay between the outward pressure from the fuel that's burning, and then the inward pressure from the gravity of all the waste product that's building up. And the idea is that eventually you'll start burning more and more fuel, and you'll have less fuel remaining, and so you'll have gravity that's pushing in still, right? But if your internal force starts losing from the external, the force of gravity, there's this tug of war, and gravity starts pushing and pressing and pressing and pressing and pressing. And so you could have either two scenarios. Scenario one, when the balloon goes pop, right? That's when you get a supernova. Or scenario two, when all that gravitational pressure just presses everything into a small, tight ball of matter. And that is the idea of the black hole. That's one of the first papers of the idea of the black hole. And have any of you seen the movie Oppenheimer? Yeah? Yeah, I quite liked it. I thought it was a pretty awesome movie. And this paper is actually mentioned in the movie. So there's a scene. I hope I'm allowed to take a screenshot from the movie. So there was a scene where, where there are a bunch of these students in a classroom, and Oppenheimer walks in, and the students yell, you've proved the existence of a black hole. And the students are all yelling and excited, and Oppenheimer is excited as well. As he's asking for Hartland. He's like, where's Hartland? Get me Hartland. He wants to celebrate with Hartland, the student that he worked on this paper with. And Hartland storms in, and Hartland doesn't look happy because he's holding the newspaper, which reads, Hitler invades Poland. So unfortunately, a war again ruins our day. It comes in and basically makes all this work about black holes get sidelined. Oppenheimer himself, he gets sidetracked. He gets incorporated to other type of science, as we might know. And his career trajectory changes forever. He never comes back to astrophysics. But I think that's also kind of something interesting, right? Because even though he's known as the father of the atomic bomb, most physicists still value his work on the gravitational collapse as one of his biggest contributions to science. His theory is still what we use now. And so hopefully now you'll remember him not just as the father of the atomic bomb, but as the person who wrote down the maths for how stars gravitationally collapse. Okay, because, oops. How are we on time?
It's 10 to 9. So.
Oh, okay, I'll start trying to wrap it up. Okay, so it took until the 60s for things to start picking up again. The war had to get over, and finally, some theorists came back to look at this idea of the, of black holes, and it was picked up by our very own Roy Kerr, our Kiwi astronomer, Stephen Hawking, and Roger Penrose. So these three pillars of science, they worked together on trying to write down the mathematical theories of these black holes a bit more in depth, more explicitly, and they showed that these black holes should not just be these theoretical curiosities, but they could actually exist. And this is actually the time when the name black hole came up. Up until now, black holes had a really lame name, in my opinion, a mouthful. It was called gravitationally completely collapsed object. Yeah. So if you guys want to know how the name black hole came up, I guess we can keep that for the Q&A session because we don't have time. Okay, yeah, I'll skip over that. And so it was only until the 70s that we finally first had our first candidate black hole. And this was from Cygnus X1. So in 71, we had Paul Merton, and he was studying X-ray sources. So X-rays, just from the sky. And we found this one source that was called Cygnus X1. And it was really bright. It was brighter in X-rays than most other objects that we saw in the night sky. And it was very confusing because stars should not have such violent X-rays. So we didn't know why it was so luminous. And we didn't know what else it could be, right? So Paul was studying this, and there was a new telescope that had just gone out called Uruhu, and it had just photographed Cygnus X1, and it had quite a few photographs. So Paul wanted Louis Webster, who was luckily his office mate at the time. So Louis was studying trajectories of stars. So she was taking pictures of stars and trying to figure out how they were moving in the night sky. And so Paul asked Louis, his office mate, for help with Cygnus X1 and trying to plot the trajectory, why is Cygnus X1 have so much X-ray? And they working together, they saw that Cygnus X1 is not actually a single object, which they previously thought, but with this new telescope, they could see that Cygnus X1 was this luminous X-ray source that was actually whizzing around something else. But this other thing was not visible on any of their telescopes. So it was whizzing around this kind of naked or like invisible object. And this was kind of mind-boggling to them, because this finally pointed to this like invisible companion, this invisible black hole. And then they realized that maybe these X-rays are coming from this black hole eating up all the material from its companion star. This is what then marks Cygnus X1 as our first candidate. And it's considered a candidate back then because it wasn't concrete proof. There could have been other things that could have generated those X-ray sources, right? It wasn't a concrete proof that it was a black hole. They just made estimates that this thing could be a black hole, but it wasn't direct. I do want to pause for a second because Louise Webster, unfortunately, she's mostly been forgotten in science. She had some medical issues and she unfortunately passed away quite young, at the age of 49. But if there's one name you remember, I hope it'll be Louise Webster, attributed to finding the first candidate black hole. But to move on, this was just a candidate. It was only until 2015, with gravitational waves, that we had our first concrete black hole event. And again, this event comes from when those two black holes were merging, and we had that sound clip that I played earlier. And I do want to highlight that, yeah, the same way when you're in the car and you hear music from the radio, it's not that it's not that you're hearing radio waves. Radio waves come to your car is then converting it into the sound waves, right? So that's what I was doing earlier as well. We often like hearing these gravitational waves, but we don't actually hear the ripples of space-time, right? But I was quite lucky because in 2015, I had just started getting into astronomy. So I was super lucky. I was like at the perfect place at the perfect time. I got an internship at LIGO in 2015. Yeah, it was super lucky. So that's me right there. Oh no. Okay. It's quite an embarrassing picture, so I'm glad it. But yeah, so these are some photos that I took. So this is the LIGO observing room. That's where we monitor a bunch of the runs. And this is the arm, the LIGO arm, in which the laser beam is shot. And oops. And actually, I'll mention this fun little story. So my first day there at the observatory, it was me and a bunch of other undergrad students, right? We were all there sitting nervously. We'd all come in really early, and we were waiting for the head of the department to come in and talk to us. And as we were sitting there nervously, the head of the department storms in, and he, the first thing he says is that, "Do you all know the LIGO dance?" And we're all like, "What?" And then he proceeds to, "I'll show you the LIGO dance." And he goes, "Oots, oots, 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 whoop." And okay, so that looks silly, but it's actually very informative. Okay, so I'll break it down and explain what he was talking about. So to understand the LIGO dance, I want us to take a look again at general relativity. So general relativity describes this kind of fabric with this object that causes this divot, right? And every time you move objects within this divot, you can generate these ripples. Okay, so hopefully that kind of makes sense. And these ripples, when they propagate, they can reach us. And these are ripples that affect space and time together. Okay, and I think the cool thing about these ripples is that they're actually, they can travel through anything and everything. They're not, like light is obstructed by matter. So like light, we can't see the outside. We can't see the night sky right now because the ceiling is above us. But gravitational waves, they don't care about the ceiling. They just pass through everything because they're intrinsically a part of space and time. So they pass through anything and everything. And that's why they're considered like the ultimate messengers, because you can see through objects with gravitational waves, right? And so we're right now being bathed in gravitational waves. And it's very small. Like, we're not feeling any massive gravitational waves, but they are coming through us. And the way we actually detect it is we have this really sensitive detector, LIGO, It took ages for it to actually work. It was built in initially 2002, and then we had to take a lot of upgrades until in 2015 they finally made the first detection. The way it works is that you have these two giant arms, right, that make up this kind of L shape, and they're 4 kilometers each. And I like to think of it as a race for light beams. So what they do is they shoot out one laser this way and one laser this way, and then because they're traveling the same distance, they're both traveling 4 kilometers, the race should always be a tie, right? Like if it's 4 kilometers, it should always be a tie. But then gravitational waves come in, and they help one of the arms cheat. They end up shortening one arm and extending one other. And then they do this, and then they do this. So that's kind of like how gravitational waves affect us. They kind of shrink one arm and extend the others. And sometimes, okay, I think I've spoken a lot. So I think to understand this material, I think everyone in this room should try to do the LIGO dance with me. Okay? I think doing helps you learn. So you'll remember it better. Okay? So people, I want you to try to, maybe you can make small interferometers. Yeah? Make a little L shape. Right? And so we're going to get a gravitational wave pass. And when a gravitational wave passes, first it'll be one arm that comes down. Other arm goes out. And then the other way. So oots, 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 and whoop. Yep. Brilliant, brilliant. You guys make excellent interferometers. Okay. Thank you for doing that dance. That was quite fun. And, okay, how much time do you have? Like 2 minutes, right? We only have...
Yeah, but don't have to finish exactly on time.
Okay. Okay, I'm going to make you guys just hear some... Okay, so I'm going to play... Is the sound, like, lowered now?
Yeah, let's try it. That's the thing. It's like it comes from a few places. So.
I'm going to play one clip of the detector data, which is not clean. So normally the clips we play for you guys, they're like cleaned.
Let's see.
Yeah, let's try it.
It's
quite staticky, right? There's actually a signal in that noise, but it's really hard to make out. So that we have to do a lot of processing. The same way, when say you're again in a car and you're trying to listen to a radio song, sometimes there's a lot of static if you're not on the correct frequency, if you're going into a tunnel. But what's cool is that if you know what you're listening to, if you know the song that you're listening to, you can still pick it out of the static, right? Kind of like, so like if there's still static and you know that there's a song, you can kind of pick it out. If you've heard other songs also before, you can kind of start making it out. So I'm going to play a clip of a real song this time. And if you guys can recognize the song or hear a song inside all the noise, please raise your hand. Yeah, you can kind of hear it, right? There's static, but you can still hear it. And I think that someone realizes the Rickroll. So yeah, you can still hear the song. And so we as astronomers, we do the same thing. We using Einstein's theories of general relativity, we simulate black holes that go like that, and we generate what their song should be. And then we try to look for those songs in the data. So this is a simulation of a binary black hole song. Can you hear? So as that's happening, I want you to visualize two black holes that are, and that whoop is when they finally merge, right? And so that's when the black holes are not spinning. They're kind of vanilla black holes that are just nicely rotating into each other. Now this next one is when we have two spinning black holes. There are two black holes that are independently spinning, like tops. So I want you to see if you can hear the difference. Can you hear that like modulation? That's actually happening because as the black holes spin, the entire plane starts spinning as well. Okay, and we'll play another final one. This is my favorite one. This time you have a really big black hole and a really small black hole. And because this one is really big and one's really small, the small one ends up being whipped around the big guy. And you'll actually be able to hear that. It's really cool. Each of those pulses is actually when it's whipping around. And you can hear it increasing. It's coming closer and closer. It sounds like a engine rotor, yeah. but you'll hear it increase in frequency. And then finally, it'll do the same. Pretty beautiful, right? Since 2015, we've had a lot of these gravitational wave events. We have about 100 so far, and secret, we're going to be releasing the new data set in about 2 weeks. It's not that much of a secret, so it's okay. I can. In the next 2 weeks, we're going to be releasing the next data set from 2020 to 2025. It's massive, guys. It's like 200 new events, right? And from these black hole events, we've already learned so much. And while I'm talking, I'll just play the clip. I've converted all of these signals into sound clips that I'll just play back to back. So that's the first gravitational wave event. Second, third, and then there's a small break. This is 2017. This is the second observing run. Each of those little bloops is a different black hole that's smashed into a different black hole. They sound different because they all come from different types of black holes. Yeah, it's a massive amount of energy. In fact, when these two black holes merge, they literally release like a large fraction of their mass in the form of gravitational waves, which eventually is what causes them to reach us. That's why they're so violent. There are these things that like literally shake the universe. Yes. I'm so glad you asked. This is one of the coolest things about our discovery in 2015. So one of the coolest things is that we learned that gravitational waves travel at the speed of light. Previously, we weren't sure. And if it didn't, then that would have broken general relativity. But we were able to see and show that these gravitational waves, when they reach us, they match Einstein's theories exactly. It's like uncanny. We're still trying to break it, in fact, because if we can break it, we can actually start moving forward and trying to figure out, more about like new theories of gravity. But still now, general relativity is awesome. And yeah, we've learned so much more, right? We've learned things like the black holes, firstly, that we've been seeing merging. They ended up being much larger than we thought. We thought that they would be much smaller, but so on this plot, each of these blue things is a black hole. You'll see that there's two black holes, and then there's an arrow to the final black hole. And so this shows you the two small black holes form into the bigger one. And it's amazing to see that there are some black holes that are going to hundreds times the mass of our sun. So it's been quite amazing, the things we've learned. We can go to what we've learned in the questions. And maybe I'll leave this also. So this, I just had a small plot to show, like, while we've learned a lot, there's still a lot more to be learned. This is our ground-based detector. We've basically found signals from these type of black holes that smash into each other. We've gotten gravitational waves from neutron stars that merge into each other. We have not got any gravitational waves from supernovae or pulsars or from the large guy and the small guy falling into each other. We haven't got any merging white dwarfs. I'm currently working on this satellite that's going to be launched in the 2030s. New Zealand is a big part of this satellite gravitational wave system that's going to be launched. We have pulsar timing detectors that are trying to study the gravitational waves from massive black holes. And basically, I just wanted to give you guys a picture that there's a lot to be learned. There's a lot of different types of sources, not just black holes that smash into each other. Anything with mass can generate gravitational waves, right? And that actually brings me to a quite prosaic and beautiful point. That these gravitational waves, it's a new field. It's creating this paradigm shift for us towards this new field of astronomy. And it's like this every time we open a new type of. Okay, so like for example, when we first used a microscope, it sparked so much new science, right? It gave us the ability to see to the microscopic world. The same way, these gravitational waves are going to be like a fundamental change in the way we do astronomy now. It's helped us study, cosmology. It's helped us study how the universe expands. It's going to help us in so many new ways that we can't even think of, and that's what I'm excited about the most. Like, every time we get a new detector out there, we end up learning things about space that we didn't even think of, right? Cygnus X1, we didn't think that there was a black hole that the Cygnus X1 was rotating around, but we figured it out because we had the telescope out there. Every time we have these new things, we kind of learn much more about the universe. And the coolest thing about these gravitational waves, right? Like anything with mass generates it. If you have mass and you move, you generate it. In fact, even we generate gravitational waves, right? And I think that's really beautiful because we're all made of matter. You're made of matter, I'm made of matter, and as we move throughout our lives, we generate gravitational waves. Every move, every choice we make is making gravitational waves. And these gravitational waves kind of propagate out from us towards the universe. And they'll continue to exist and move throughout the universe until the end of time. And so for me, the very first time I got on a bicycle and my sister taught me how to ride a cycle, that's written in the fabric of the universe. That's written in space-time. For me, when I first entered the LIGO lab, and when you all did the LIGO dance, that's written in space-time. It's forever etched there, right? And I think it's kind of beautiful that our entire history, from our very first steps to our first kiss to the last time we'll close our eyes, every moment in our lives is written in space-time, and it's going to be propagating out there forever, adding to the cosmic symphony. And I think that's such a beautiful way to think that our choices in our lives, they matter. They're affecting the universe. They're literally traveling away from us in the cosmos at the speed of light, reaching these very black holes that we've been talking about. So hopefully, I would love if you guys would remember that our choices matter, and they're written in the universe. So yeah, thank you.
Thank you.
I'm so sorry, I'm like 8 minutes over. Yeah. So I saw that you had a question.
Yes. You said that when black holes merge, they lose a large amount of their matter into gravitational waves. And then you said when we move, we create gravitational waves. Does that mean that when we move, we're actually losing matter to the gravitational
Really
waves?
good question. So it's to do with, so do you remember that equation E is equal to mc squared? So that basically says that energy is equal to mass times the speed of light squared. So when these two black holes merge, they actually change some of their mass into raw energy. Now, this actually works also when we move around. We're in a way moving our mass, and the same way, when you rub your hands together, you generate heat energy, right? But you also, in a way, generate very, 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 very tiny ripples in the fabric of the universe. So some of that energy that you generate when you move around creates gravitational waves. And okay, I will say it's very tiny. So it'll be like amazing if someone can actually detect it. Like there's sci-fi books about how people can communicate with gravitational waves, but it's going to be tricky until we get there. But
Probably the concept of telepathy is maybe distinct.
oh, maybe, yeah, I'm not sure.
Yeah, could be. There is a chance.
I'm not sure, yeah.
Nobody is sure until that is.
If the light can't escape the black hole, the two black holes, how does the energy escape the two black holes?
Really good question. So it's to do with, again, I guess it's to do with the equations that Schwarzschild described. So when you think of a black hole, firstly, I think I'd like to highlight again that I don't like to think of black holes like holes, right? They're like more like these balls of matter that have so much stuff that it's just that the gravitational pull from it is so much that light can't escape from it, right? But there's a boundary. There's a boundary at which that happens. And anything beyond that boundary, it's fair game. So as soon as, that's actually why, okay, so I don't think I mentioned this properly, but like, the X-rays that we got from Cygnus X1, they're the brightest things in the universe. So black holes end up being some of the brightest things in the universe, not because of them themselves, but because of the stuff they do to their environment. So when black holes sit in the centers of these galaxies, they have like clouds of gas around them, and they start sucking in the clouds of gas, right? But the gas doesn't like fall in straight. The same way when you have water in a bathtub, yeah, when you have water in a bathtub, you'll see that it starts spiraling in, right? And it spirals in. It doesn't just go straight in. And yeah, exactly. So everything before the event horizon starts spiraling in, and as it spirals, it's it's creating so much friction because it's turning and turning, and it's being accelerated so fast because that spiral is really strong, and that spiral creates so much heat that it literally lights up the sky like nothing else. And so these black holes end up being the brightest things in the night sky. These are called quasars. And to answer your question about gravitational waves getting emitted, it's the same thing. It's like, like these things are moving in space. And do I have the animation? Yeah, I like thinking of space like the fabric. And as you move this object through like molasses, you generate these ripples that propagate outwards. And that's also why I think they're the greatest ways of trying to study black holes. Because as they move, they capture all the information that helps us learn about them. They tell us the trajectory of the black holes. That's what we hear. The sound we hear is the trajectory of the two black holes spiraling in. Okay, I hope that answered. Oh, sorry.
Because the masses is getting smaller because some of the masses being converted into energy, which drives the gravitational wave.
The mass, it really only becomes smaller when the gravitational waves initially when it's circling, that's actually only helping reduce its speed.
Yeah.
So in the rotation, it's losing energy in the form of gravitational wave, and that's causing it to slow down or start spiraling inwards.
But there's a mass conversion.
And then when the collision happens, then it's all sort of weird physics that we don't quite understand, but we do know one thing, which is that in that picture of the black holes that we saw, we get two black holes that merge, and the final black hole, so say you have 5 plus 5, it's not necessarily 10. Because some of that mass in energy.
Yeah, and leads to black holes. Unlike the light which can't.
Ah, good question. Yeah, I think you were hitting on something that we don't quite understand yet.
Yeah,
So,
well,
yeah. Sorry, you had a question?
These black holes emerging, are these holes wandering around in the universe, or do they actually occur in pairs?
Very, very good question. I think it's over.
If they're wandering around, there must be a few stars on the way.
Yeah, perfect question. So there's a bunch of different types or categories of black holes, right? And the ones that we've been seeing, firstly, we weren't sure that they would even exist before we heard them, like before the 2015 detection. So the idea is that you could have stars that form, and we know that stars can form in two. We've seen it with our telescopes. We've seen binary systems. We have it in like Star Wars as well, but I don't know. So the idea is that when stars evolve, you could have kind of like this sweet spot where some stars evolve such that they can grow and they can collapse into a black hole, and they can still keep on orbiting the other star. And then the other star also grows and collapses into a black hole. Then you have two black holes that are spiraling in. There are some other questions though, like for example, these stars are normally quite far separated. What brings them in together? That's still unknown. So, yeah.
What's the explanation for the paradox you opened with the disappearing sun? Faster than the speed of light action.
Sorry, the faster.
What's your explanation for that paradox?
When you whip away the sun, what is the explanation there?
Oh, so that was just like a thought experiment. So if you remove the sun, it basically goes to show that the theory of Newtonian gravity doesn't work, right? Because that's like an instantaneous force. So according to the new theory of gravity, there would be 8 minutes before the idea of gravity reaching us. It's almost like, so say you have the trampoline, and then you jump up. There's going to be, the trampoline is going to react and create this ripple, and that ripple will eventually propagate and tell the Earth that, hey, there's, yeah. It's
really the flattening of that space-time curve. So the time it takes for the space-time to flatten out.
Yeah.
If it's flat, then we go in a straight line.
Very. So when there's no mass, we call it the basic metric. So yeah, the Newtonian metric. Yeah.
Just one other, sorry.
Oh, I've just got a question about, there should be, like you've got the signals that you're picking up at these mergers, but there should be a general background of gravitational waves, but your detector is picking up quite a lot of noise. So do they know if the background is measurable yet, or is there still too much noise to measure the background?
I love this question because this is actually something I do work on. So, so I think this brings us again back to So I think what you're hitting at is that, yeah, the universe is massive. There's many black holes. There's many black holes that should be merging all together at all times, right? And they generate these ripples that should be reaching us on Earth. In a way, right now, our detectors are only being able to hear the loudest claps, right? We hear the claps, and then what we do is we have 2 detectors. We actually have about 4 detectors, but 2 of them work the best. And we try to hear if the clap occurs at both detectors around the same time. And we then try to see independently, is the sound, the signal coming from the same location in the sky? Do they have the, the same, songwriter? And try to work it back that way. The question you're asking is also like there is this cosmic hum, right? And that's actually what that's what these guys are trying to look at. The pulsar timing array, it's a beautiful experiment. They basically studied these types of stars known as pulsars. So they built this 3D net meshwork. So it's almost like 3D connect the dots that they've done throughout our Milky Way. So you can imagine that they've kind of dotted all these pulsars out and they've connected the dots between them. And the idea is that if there's like these gravitational waves from a really long wavelength, like a really large term, from say something like the Big Bang, then all this 3D net meshwork should be breathing. It should almost be like contracting and expanding in the same way. And just in 2023, they showed that there's strong support for this. They can't be conclusive yet because as scientists, we like to have things that are very, very certain. But they're showing that we're building up. It's still like the hazy outline, but we can see an outline now that there is this kind of breathing oscillation from a background. Yeah.
How's the LIGO funding going now with the cuts to science?
Yeah. It kind of really does suck. It's they had to cut the observing run short, so we ended our observing because the detectors require money to operate. The detectors require staff and scientists to work and make them run. But the U.S. funding situation has been bad, and we've had to cut it short. And we don't know what the next observing run is going to look like. It really does frustrate me so much because NASA has now pulled out of this mission. This mission is going to be amazing. It's going to be 3 satellites in space shooting a laser beam 2.5 million kilometers apart at each other. That's like a crazy feat of engineering in itself. And NASA initially was funding this. In 2016, they launched what's called the LISA Pathfinder. So they had 2 satellites shooting a laser beam 2.5 million kilometers, and it worked. They were able to shoot it, right? But it wasn't, we weren't able to do too much science for it. It was a test case, so it was really cheap. And the plan was in 2035 for this to launch as a joint international collaboration mission. So the European Space Agency, New Zealand, folks in India, folks in China, folks in the US, we were all going to come together, work on this instrument. NASA has now pulled out. New Zealand is still, I'm working with a team in University of Auckland and with people in Otago to help build up the song detection algorithms. But the US and the Europeans were in charge mostly for the building of the instrument. But now that the US is pulling out, yeah, so again, politics is really lame. Yeah.
Like the war happened in Africa, that sort of thing.
Yeah, exactly. It's always something, right? Politics and war and human stuff. Yeah.
Can we build a ship that grafting lies on graph.
Yeah, so I think I've read some sci-fi descriptions of this, and I think it would be so cool to do this, right? But unfortunately, I don't think we're quite there yet. If we were there, that would be, like, our grasp of physics would be so much better. But see, this is why we should continue funding science. If we could fund science, I'm sure we'd be able to build a cool spaceship which serves gravitational waves. Maybe not in the next 10 years, but hopefully. So not yet, but I dream. So will I.
One last question. Your LIGO arms, 4 kilometers long. Are they raised about 1.5 meters up the ground to counteract the temperature?
Yes, yes.
1.5 meters?
I'm not sure what the exact, but like, yeah, I was just talking to my partner about this earlier today, that is such an amazing feat of engineering in itself. That instrument, for the longest time, it was basically just a glorified seismometer, because all it was detecting was vibrations, not just from the earth shaking, but from people walking, from even like things like, you know, like, okay, in the US is a special case, right? There's like not just like birds pecking at the detector, but some people have come with shotguns and shot the detector. So we've seen that in the data. But yeah, the engineering for this thing has been amazing. We've had to detect, like, develop new types of laser beams to shoot the laser that's strong enough to hit these mirrors. We need to actuate the mirrors to counteract seismic activity. So because there's, you know, like, Earth is not stationary at all, we need to get these mirrors to kind of counteract that. So we want them, like, ideally we'd have this in space, which is why we're building the next one in space. But we have to do all this stuff to kind of keep the mirrors stationary. We need to account for the fact that the photons that are hitting the mirror can move the mirror. We need to account for the fact that as the photons hit the mirror, they impart energy, which heats up the surface, causing the mirror's surface to no longer be flat, but like wavy. And so we have to do like cryogenic cooling on these mirrors. The engineers are just, yeah. I'll let you guys find this out on your own. The name of the black hole, you guys should Google it. It's not trivial. And I want to leave this on. Mitchell wrote a poem on gravitational waves. So.
Yes. Oh, okay, right. So a bit of context for this. In 2016, I was an undergraduate student studying under Jane Outridge, and one of the assignments she set us during the course, because this, of course, was when the big discovery kind of came out. There were tons of papers being published about it, and what she got us to do was to summarize or review 2 of those papers. And one option that she gave us was, she said, you may, if you wish, write the summary in the form of a poem. So, you know, not to be outdone, I wrote a sonnet. But yes, I mean, I can recite it if you like, but it's, yeah. Basically, my attempt. I did actually write a full review just in case that didn't hedge my bets a little bit. But yeah, it just kind of trying to capture essentially what such a massive breakthrough it was at the time, and of course going on since. So many more discoveries that have been made. I just want to say thank you so much, Avi. One of the things I love so much is seeing knowledgeable people talk about their passions, and you know, your excitements, especially as we started talking about your research and things that you are excited about, is really, really infectious. And I think everyone here has really enjoyed hearing you speak. We'd love to have you back again sometime to talk about further developments, because they seem like they're coming thick and fast. So thank you so much. We do have a little gift for you. Hopefully it will come in useful on your next trip up to the pinnacles. But yes, thank you so much on behalf of the Society.
Thank you so much.